Okay. So welcome to the second session of this morning. And it's my pleasure to introduce the talk, Can we formalize type theory intrinsically without any compromise? A case study in Cubical Agda by Fredrik.
Right, thank you. Just waiting for the slides to magically appear. There we go. Right, thank you for coming. So this is joint work with Liang-Ting Chen and Tsai from Academia Sinica. And we just learned in the business meeting that this is one of the very few Agda talks at CPP. But I hope there's not going to be too many Agda details, so that is understandable anyway. So what's the motivation? Well, if you want to do formalized metatheory or you want to do formalized metaprogramming in general, then you need to have some kind of internal representation of the syntax you're manipulating or proving things about, right? So we are trying to get a nice economic way to get this internal representation of the syntax of type theory. And besides, if you really think that type theory is an adequate foundation of mathematics, then it certainly should be the case that type theory should be able to reason about the syntax of type theory, because that's also part of mathematics, right? So concretely what we want is we want to have a type whose elements are terms which are well-typed in a certain context gamma of a certain type A. And it should only contain these well-typed terms rather than just having some extra junk that you don't want to reason about because it doesn't really make sense, right? So why is this hard? Well, if you just do this for simple types, then it's not. But if you do it for dependent types, then there are many complications. So for example, if you have dependent types, then they only really make sense in a context, right? So the type phin n of a finite type with n elements only really makes sense if you know that n is a natural number. If n is a Boolean, this makes no sense. And of course, terms depend on types. But if you have dependent types, then types also depends on terms. So you have this circular dependency between all the different sorts, where we have types depending on terms, depending on types, depending on substitutions, and all these kind of things. So you have to do everything at once. You can't stratify it in a nice way. And you also need to worry about definitional equality between types, because if you have a type such as fin 1 plus 1, then you only really know what the terms of this are after you've computed what that 1 plus 1 is 2, so you know that you're talking about two-element types, right? So this also needs to be part of your syntax somehow. And similarly, if you have something like a substitution, an application, a dependent function applied to an argument, then you're going to end up with a substitution in your type of that thing. So you also need to have substitutions in your syntax. And this then leads to a non-trivial equational theory of these things, because you would expect that if you substitute by the identity substitution, that should really do nothing, right? So all of this needs to be part of the problems. So how have people done this before? Well, this is quite a selective history, I guess, but if you go back to the last century, then there was an early formalization by James McKenna and Randy Pollack, where they represented pure type systems in an old system called Lego. And what they did was they basically took all the untyped terms, and then they had a predicate that said, these are the good ones, these are the well-typed ones, and you just form a sigma type to keep these. And then you have to prove a lot of lemmas where you say that, well, actually this case can never happen because it's well-typed by this separate thing, right? But it's also what they did in the SynFlean project that we heard about yesterday. And I think that that's probably a good way to do it in Lean. But if you're doing it in Agda where you have nice inductive families, then you can hope to do better, right? So Nisse Danielsson did something like this in a precursor to Agda called Agda Lite, where it had an explicit equality relation, and then he proved that all of constructions you do actually respects this equality relation. So this is a classic instance of setoid hell, right? Where you have a setoid of terms, and then you explicitly have to prove that whatever you do actually respects this. And Chapman did basically the same thing, but he managed to simplify it a little bit and only use inductive-inductive definitions rather than inductive-inductive-recursive, something like this. But he still had to do this manual proof effort where he had to prove that everything he did actually respected the equalities, right? So I would say that the breakthrough happened in 2016 when Torsten Altenkirch and Ambrish Kaposi realized that you can use quotient inductive-inductive types from Honda-Type type theory to do a lot of these things for you instead, right? So the idea is that use the quotient feature of homotopy type theory to make the definitional equality of the object theory really be the real equality of the meta theory, right? Which then means that all constructions automatically respect this equality. You don't have to prove separately that whatever you do respects it. Just because it's equality, everything respects equality, right? It also means that you can't do things differently for things that should be equal, which I would argue is a feature. If you're actually printing terms, you might not agree with me, but if you do meta theory of things, then I think it's definitely a feature, right? So how can we understand this? So it's a big definition, and one way to understand it is that you can make sense of it as saying that, well, what they did was they took the initial category with families, which is a certain model of type theory, and they encoded it as a quotient inductive-inductive type, right? Which gives some kind of guarantee that this is a sensible thing to do. And in particular, we know that categories with families, these kind of models, they are an instance of a generalized algebraic theory, and we know that every generalized algebraic theory has an initial model. So it makes sense that you could do something like this. And what they did this before Cubical Agda was a thing, so they did it in kind of standard Agda with postulates, where you very carefully postulate the equalities you want for your quotient constructors, and then you define an eliminator, and you hide this behind some abstract thing, and you promise to never look at the explicit representation. And this worked very well, but now we have Cubical Agda, we have support for quotient inductive-inductive types, so we could hope that we could just do it without any tricks. So that's what we set out to do. But if you do this, you realize that in practice, this is not as straightforward as you might think, right? So here's just one example of what you have to worry about. So if you look at the equations for a category with families, then it's a category with families, and then you have an action of substitutions on your, so the category represents the substitutions, and then you have a family of types and terms. And you have equations like this, which says that, well, if you have a type A and you act on it with the identity substitution, then you should just get A back, right? And similarly, if you have a term T and you act on that with the identity substitution, then you should just get the same T back. But if you think about this equation here, then you realize that the left-hand side actually has this type. So it's a term in context gamma of type A where you act on it with the identity substitution. And the right-hand side has type just, it's a term of type in context gamma of type A. So they don't have the same type unless you apply this, you use this equality to make sure that they have the same type, right? Which is fine in extensional type theory, say, but if you just want to do this in Cubical Agda, for example, then you need to have an explicit transport here where you use this equality proof to make sure that things line up and you're in the same type, right? But unfortunately, if you do this in Cubical Agda, then Cubical Agda will, for some reason, say that this is not a strictly positive definition, which of course is nonsense. Because there's nothing non-strictly positive about this. But, I mean, you can vent and scream at your screen, but in the end, you want it to work, so we need to do something about this, right? So, in this particular case, we could use Cubical Agda's built-in notion of a dependent path instead. But I think that then we're starting to stray from this idea of using the categories with families formulation, because that's a Cubical Agda specific thing, right? So it would be nice if we could do this in a more principled way. Okay, so why do we need this transport? Well, it's because we're trying to be really precise about the types of our, the things we are manipulating. So for example, if we look at the constructor for taking a substitution from gamma to delta and extending it with one term to substitute for the top variable in order to get a substitution into an extended context, then we insist that this term we have here really is of a specific type, right? We're only happy to substitute from gamma to this extended context if we have a term which fits with this type that we are extending the context with, right? So that's where our problem's coming from, that we are really trying to be precise about these things. But of course, we could equivalently, we could say, well, you can give me any term you want, as long as you also give me a proof that it has the right type, right? So this is the Henry Ford principle. You can have any car you want as long as it's black, right? But the point is that if you do this, then we used to have a transport here. But if you do this, now we have this explicit equality proof, then the transport disappears, and we're just carrying around this equality proof instead, right? Which makes Cubical Agda happy because there's nothing There's nothing weird going on anymore with a function in the middle of our definition, right? But if we now do this everywhere, then really we don't need to keep this equality here around locally. We can just drop all of these things, which removes the problems, but then we reintroduce them by having a function type of, which says for every term what its type is, right? And then here we would change this to a constraint saying that, well, the type of t better be this thing, right? So this is what you end up with if you do this. So we have this simultaneous definition of context, substitutions, types, and terms. And compared to the previous definition, we are dropping the indexing of the terms of the types, but we're reintroducing it with this function here, right? And I've written set to mean set in the sense of homotopy type theory. So it doesn't have any higher power constructors, but the context can be any type. And if you do this, then you realize that you end up with something that looks quite a lot like another equivalent notion of a model of type theory, which is the so-called natural model, which we also briefly saw yesterday in the talk about Symfleen, right? Where we have a pre-sheaf, two pre-sheaves, and a natural transformation between them. So it's nice that this still has some kind of foundational grounding in the models. So this is what you end up with, and it's of course too much to take in at once. So I've highlighted the differences compared to the previous definition. There's not that many of them. Let me talk through them. So the first one is that we have this type constraint in our extension. We notice that there are no transports appearing anywhere on this screen, which is nice. And we also had to introduce some seemingly extra equations here in some of the constructors that are derivable from other equations, but if we put this derivation in, then we still get this strictly positivity error because we don't have a function in the middle of our definition. So we just say, okay, give me any proof of this you want. And because we have explicitly asked for everything to be a set, there's at most one proof of any equation anyways. We know that it's equal to the canonical one, right? And we also have to interleave the definition of this Tsai function so that this definitional equality here is available when we define this eta law, for example. Right? So we can write REFL here. Okay, so that's just for the basic type theory, just substitution calculus, more or less. But in the same way we can do it, we can add pi types, we can add inductive types as the Booleans, we can add a universe, and it all works quite well, right? One small thing that you have to do as well is that we found it useful to add in other kind of tie-off proofs that they should be derivable, but you can construct them from other pieces, like I said. So for example, if you have a context which has a Boolean as the top variable, and you ask for its type, then that should be the Booleans where you can put in any substitution you want, because you know that substituting the Booleans by anything is just going to be the Booleans, right? But sometimes you want it to be something that's not quite the Booleans, which you could fix up, but if you just put it in like this, then we know that it's going to be equal to the canonical proof for this fact anyway. So again, it's just about keeping the strict positivity checker happy, right? Okay, so we have a data type, but anyone can write a data type. So in order to see that this is the right data type, you would expect to at least be able to show that you have an initiality property, that you have some kind of morphism of models from this data type to any other model, right? And you can use the pattern matching or cubical Agda to define these things. So you get recursion principles, you get induction principles with witnesses that this is the initial model, right? Annoyingly, this is the one thing I'm not so happy about with this, is that we still have to mark these recursion principles as terminating when we did this, even though they are kind of obviously terminating. Because all the recursive calls are on smaller things, but I think the problem is that we also had to prove this kind of naturality property at the same time. It's just that it doesn't matter if you first translate the term and then you use the tie-off of the model, or if you first use the tie-off of the syntax and then translate the type, right? That should be the same thing, and you can prove this. But then here you have a rect tie of B, where B is something completely irrelevant to the thing you're currently using. So I think that's why it's not. Cubical Agda doesn't see this as obviously structurally smaller, annoyingly. But we mark it as terminating, and then we use this. And and it does terminate in practice. And we also thought that, okay, so we have these kind of hacks along the way, but when we present it as a recursion principle to the user, we can just define away these hacks, and it will be a nice interface. But actually, it turns out that it's not a good idea to do this. It's better to let the user also do their own hacks if they want, because sometimes you can then give a more direct definition that doesn't use this constructed proof if your situation is easier, which makes some other constructions easier. Right. So what can you do with this? So here's one example. You can construct the standard model where you interpret context as types, and types in context gamma as functions from gamma into type, and substitutions as functions. And then for terms, you can switch to the fibered perspective again. We say that, well, a term in context gamma, well, that's going to be an interpretation of a type. And then for every element in your context, you have to give an element of that type, right? And then the Tsai function is just the first projection that picks this out again. But we have to do this, we have to assume uniqueness of identity proofs, because otherwise we're not allowed to go into this non-set, right, from a set. Similarly, you can define the term model if you want, where just everything is interpreted as itself. Works quite well. Other things we tried was to actually do normalization by evaluation for this syntax, just for the substitution calculus, and that worked very well. Maybe in part because Gene did it. I don't know where he is. So it worked very well because there are no transports anywhere in these terms, so everything just computes. So transports are they're bad in many ways, but in particular they stop some computation in Cubical Agda. But because we get rid of all the transports, this just computes, and it's very nice. We also tried to do the logical predicates model, where the idea is that you start with a model, and you want another model which is displayed over this one, which means that for every element of the first model, you give an element of your new model. And then if you look in the literature, you see that, well, a logical predicate model, if you want the types over a type A from your original model, well, they should be types in an extended context where you now have access to a variable of this type as well, right? So this is like a predicate over A in the sense that it's a type with a free variable with an element from A, right? So you can try to define this. I've simplified it a little bit because you need to cryptify it to deal with the context. But the problem now is that we now have types, the type A appearing in our definition of the terms again, right? And now we have the transports coming back into our terms, and then we're back to basically the same kind of equations we had before. So this trick we used to get rid of the transport does not help for constructing this particular model construction, unfortunately. And you could try to use strictification to get rid of this. And all of the strictification machinery that Ambrus Kapose and Priya developed, it's a very nice paper. All this also works in this setting, if you kind of translate it across. So that's nice, but unfortunately it only deals with kind of the basic structure. It doesn't deal with pi types, for example, and it's with the other more involved type formats that you really start to get into problems here. So even though strictification works, it doesn't help with this thing. So unfortunately, I guess there's no silver bullet, right? So to summarize, some things work well, some things doesn't work so well, and some things kind of works, but it's not enough. Okay, so to summarize, we developed a representation of the syntax of type theory in type theory. I would say it's inspired by natural models rather than categories with families, just to give it a foundational grounding. But the main idea is that we have this Tsai function rather than indexing the terms over the types. And the good news is that it leads to fewer transports, which makes it easier to actually get Cubical Agda to accept this. The bad news is that when you actually do things with this, then the same kind of transport seems to creep in again, and it doesn't solve all your problems, even though it at least lets you get there. So to answer the question in the title, can we formalize type theory intrinsically without any compromise? I would say not yet. Thank you.
Do you have questions?
You said that your contexts were in type, whereas everything else was in set, but they only contain types which are in set, right? In the syntax.
Yes.
So you could also lower the universe for context, for the syntax.
No? So the contexts in general I allow to be anywhere. They are unrestricted, right? Everything else I need to restrict to be a set.
But they could be restricted and it would still type check, right?
Yes.
Yes.
It's more of a feature that you don't need to restrict it. I mean, it's the same way when you define the notion of a category. You typically want your hom sets to be sets, but you can allow your objects to be anything, right?
But it also means that there is no binding for a context in any of the constructors. It's a parameter.
Except parameter, yes, that's true. Yeah.
Okay.
Can the next speaker come to set up while we are still asking questions?
Thanks for the nice talk. For determining, like, do you have some intuition? What would it take to get rid of it? Probably you need to modify Cubical Agda, but is it realistic to prove these neutrality properties on the fly during the definition of a type?
That's a good question. I'm not sure. I mean, I think the thing you would like to do is I'm not sure if you remember how we formulated. We said that if you had an equality, then you got another equality. And I think what you would really like to do is to just inline that equality in the second one. And then I think it would be possible to prove it or just get it intrinsically. But it doesn't play well with the rest of our formalization, unfortunately. So, but yes, I mean, it would be nice if we could do something.
One last question.
Yes. Thanks for the talk. So I was wondering, so we've been telling to mathematicians for a long time that presenting fibrations in a fibered way is kind of annoying, and it's much better to present it in an indexed way. And basically what you're saying is that actually maybe we were wrong all the time. Is this a more general lesson, or like is this a particular instance, or like what do you make of this question?
I think, unfortunately, the answer is that sometimes you do it one way and other times you do it the other way. Right?
And do you have ideas of like when is one superior to the other, or like some sort of general lessons that would apply outside of QIITs?
No, I mean, yeah, that's a good question, of course. I mean, I guess you try it one way, and if it doesn't work, you try it the other way.
Fair enough. Thank you.
Okay, one last question by me. Oh, so okay, I'll ask it offline. Thank you very much again.
Thank you.